Okay, welcome. We are here for day 2 of our heat calculations, and today we're going to be looking at calorimetry. But before we start that, I want you guys to think a little bit more about what we said yesterday, the difference between heat and temperature. So the first question I want to pose to you, which has a greater temperature? If we had a cup of boiling water or a swimming pool of boiling water. And I am doing this without students in the classroom, so I'm not going to wait for anybody's response. But you know it is boiling water, so what that means is you've got 100 degrees Celsius. It doesn't matter. They are going to be the same in both of those situations. But if we were talking about heat, remember that mass, if I were to do mc delta T, or if I were even to look at some formulas like that, that mass is a component of heat energy. So what has greater heat, a cup of boiling water or a swimming pool of boiling water? We would go with the swimming pool because it does have a greater mass. Okay, now we're starting with our calorimetry, and what this is a science associated with determining the changes in energy of a system by measuring the heat exchanged with the surroundings. So we use a system called calorimetry, and we're going to do a lab on this today, on the same day. And basically we can do a lab and use calorimetry to be able to determine the heat of the reaction, the heat of fusion, maybe the specific heat capacity of a metal. That's what we're going to be doing in our lab. You could also do something like this to figure out your change, actually not your change, but your final temperature of the water and the metal. So there's a couple different things that you could use this for. And the way it's set up is that you have some sort of insulated coffee cup. That's why they call it coffee cup calorimetry. You've got this insulated cup, and we are going to start with two different substances. We are going to start with a metal. Notice that it's really hot, and we're also going to start with water that is much colder. So when we put those two things together, you take that hot metal and put it into cold water, the hot metal is going to lose some of its heat energy, and the cold water is going to gain some of its heat energy. I probably should have written a Q there. And because of that, eventually the two are going to reach that same temperature, and we can just do the math that's involved in going ahead and figuring out our missing variable. So what we need to remember is that our heat lost is going to be equal to the heat gained. But because we're talking about lost and gained, you have to remember to put that negative sign with the substance that loses the heat. And that's what is listed down here. Remember, heat lost is a negative and heat gained is a positive. In this situation and in most of these situations where we're working with a metal and water, the metal is the one that starts off hot, so that's the one losing that heat energy, and the water is what gains it. So really what that means is when we set this up, we're going to be able to set it up to where we say mc delta T lost, that loses the heat, is equal to the mc delta T that gains the heat. So that's what we will be doing, and it all becomes one big algebra problem. So first example, here we start with 25 grams of iron, and we're told the specific heat value, and it's initially at 225 degrees Celsius, so that's pretty warm. And what happens is it's dropped into 75 grams of water that's initially at 25 degrees Celsius, so that's much colder. Here we can see what happens. This is going to need to lose our energy. This is going to need to gain energy. So to remind us, heat lost equals heat gained. We're going to be looking at heat lost for iron is equal to heat gained by the water. So negative mc delta T for our iron is equal to, mc delta T for our water. You don't really have to write all of that down each time, but I just wanted to show you that right up front. Okay, so now it becomes a messy algebra problem. I'm going to start with my iron, and I see that I've got 25 grams. So I'm going to go ahead and throw in, I'm not going to write my units on this, but I've got my 25 grams. I put a negative out there. Specific heat for my iron is 0.452 joules per gram degree Celsius times my change in temperature. And by the way, that's what I'm looking for, is my final temperature. I'm given everything else except my final temperature. So these are probably the worst of the math problems because you've got a subtraction in there as well. So remember, your change in temperature is your final minus initial. So we set it up like this, and that's going to be equal to the same formula for our water. So our mass of our water is 75 grams times our specific heat of water is 4.18 joules per gram degree Celsius. And then again, we're looking for our final temperature for our water. So it's final minus initial, and our initial is 25 degrees Celsius. So all we have to do is solve for TF in this case. So I'm going to just be quiet and go through and show you the math that I've got set up on this. And then finally, that last little bit, we get our final temperature is equal to 31.96. So if we want to go ahead and take that just to those whole numbers like we've got in our problem, that's going to be 32 degrees Celsius. Okay, hopefully you were able to get through that okay. That was a tricky little math there. Okay, next one. Here we've got a block of aluminum, and we're told specific heat and initial temperature. It's dropped into our mass of water, and we know specific heat and temperature, and we know the final temperature of the whole entire system. We want to find the original mass, or the mass of the aluminum block. So we know in this case that aluminum is losing and water is gaining. So we are looking for mass. So if you want, you could just set it up like that. You're solving for your mass. You know your specific heat of your aluminum. So that's what I'm working on right now, is my aluminum side. And then we know our change in temperature. Your final is 25.5. Your initial is 185. You set that up equal to the water side. So your mass of water is 165 grams. Specific heat, 4.18 joules per gram degrees Celsius. And your change in temperature, final, the whole system, reaches a temperature of 25.5 minus our initial of 23. The math is a little easier. And we get that M equals 12.052. And it looks like we should probably round this to 3 significant figures. So let's say that the mass of our aluminum equals 12.1 grams. All right, feel free to pause as needed, but I am going to move on to our last one. And in this one, we have a block of unknown metal, and I think you might, on your notes, you might have this omitted, so make sure you add that in if it's not added already. So a 7.95 gram block of an unknown metal initially starts at 243 degrees Celsius. It's dropped into a coffee cup calorimeter containing 115 grams at 27 degrees Celsius. We know the final temperature of the system is 29.3 degrees Celsius. We want to solve for the specific heat of the metal. This sounds really similar to what you're going to see in lab. So here we've got the negative heat loss. The heat loss, so negative Q value for your metal, is equal to that heat energy gained by your water. So we've got negative 7.95, that's grams, times our specific heat, that's what we're going to solve for, times our change in temperature, so the final is 29.3, minus our initial of 243, so it was a really hot piece of metal, and we threw that into water, 115 grams of water with a specific heat of 4.18 joules per gram degrees Celsius, and the change in temperature reached a final temperature of 29.3, and it started off as 27 degrees Celsius. So when we solve for C, we end up getting just kind of throwing down a bunch of numbers that are in my calculator. But when I solve for this, my final answer, rounded to 3 significant figures, is my specific heat is 0.651 joules per gram degrees Celsius. There you go. If you like math, this is your unit.